Hello Year 10. Today's lesson is about energy efficiency. You'll notice from the first page of this video that it looks all very green, doesn't it? Environmentally friendly. And that's because energy efficiency is good for the environment. It means that we waste less energy and more of the energy we use is transferred usefully, which is better for the environment. Okay, so let's move on and look at the next slide. So let's go back to basics for a moment. The law of conservation of energy states, and you've got to learn this, folks, energy cannot be created or destroyed. It can be transferred from one energy type to another. Okay, so that is really important. You've got to just learn that. Okay. The consequence of that is that the total energy input must equal the total energy output. We can be a little bit more specific than that. Okay, so the next box says that the total energy input equals the wasted energy output plus the useful energy output. So if we look at this diagram of a bulb down here, we have got the total energy input, which is electrical. Okay, the wasted energy from a bulb is the heat. The useful energy output from a bulb is the light. Okay, so the total electrical input must equal the heat output and the light output. There's another example over here. The cyclist going up the hill. I'm not going to say too much about this, but just that at every stage, heat energy is being wasted. So it's not an efficient process. None of these things are efficient because heat energy is always wasted. Okay, let's move on. So what is efficiency? Efficiency tells us how much energy is usefully converted, and that's the key word, usefully converted. No system is ever 100% efficient. Some energy is always wasted to the environment as heat energy. So here are the two equations. You'll note there are two, and these are given on the formula sheet. Efficiency is the useful energy output divided by the total energy input, or efficiency can be calculated by dividing the useful power output by the total power input. Multiplying by 100 is optional. We don't have to do that. You can just leave it without multiplying it by 100. If you don't multiply by 100, then your efficiency will be a decimal with a value between 0 and 1. Demonstrate that as we go through this video. So here are some examples. Okay, here are some examples. We start with the candle. Now the total energy input is 8 joules. The useful light output is 2. The wasted heat output is 6. You'll notice that wasted heat energy is always quite big. Yeah, so a candle is not very efficient. We're going to divide the useful, which is 2, divided by the total input, which is 8. We get an efficiency of 0.25. You can leave it like that. We do not need to convert that to a percentage. Okay, but sometimes the question says convert to a percentage, so you just multiply that by 100 and you get 25%. Let's look at the next example. Okay, so we've got a TV down here. 95 joules of electrical energy input, 80 joules wasted as heat, 10 joules as light, 5 joules as sound. So the total there is 15. Okay, so if we look at the efficiency of that, the total useful output is 15. The total input was 95, so 15 divided by 95 is 0.16. And if we convert that to a percentage, that is 16%. Okay, you don't have to convert it to a percentage unless the question asks. Now you'll notice that we're never going to get a percentage higher than 100%. You can never have an efficiency more than 100%, which means that your efficiency can never be higher than 1. Okay, So let's have a look at some examples here. Now we're going to start off nice and simple. We've got a light bulb at the top there. The energy in is electrical. Okay, electrical energy in. The useful energy out is light. The wasted energy out is heat. Okay, sorry about my very poor writing. Now we've got a missing value here. So we know that 355 joules goes in. Okay, so we've got 355 going in, 35 useful. How would you work out that number? Well, it must be 355 minus 35, 320. Must be 320 because the two numbers output must equal the input. Okay, let's look at the next one down. Electrical heater, well, it's electrical energy going in. Okay, and we've got, well, the useful energy out this time is heat. Wasted energy out, well, it probably makes a little bit of sound. Well, our heater does. So we've got to work out this this value here. So let's do a little sum. It's going to be 673 minus 465 equals, get my calculator out. You might be able to do this with mental maths. 673 minus 465 equals 208. Okay, so let's go back to the normal pen again. That's 208. Okay, so a few examples there. Let's make that a little. Okay, let's consider the energy changes taking place in each of these situations and then work out the efficiency. So let's get my pen. We've got a car at the top here. We've got 1,500 of useful energy output. Now that must be kinetic energy, mustn't it? Because the car moves, a useful car does anyway. The wasted energy output of a car, well, the engine gets very hot, so that will be heat. And according to this, it's 4,000 joules. Okay, now I've got a missing value over here. Let's see if we can calculate it. We know that the fuel for a car is chemical energy, and it must be 5,500 in total, because if we add 1,500 to 4,000, we get 5,500. So let's work out the efficiency. The efficiency, I can't write it all in there, not enough space. Well, it's the useful output, which is 1,500 divided by 5,500, and we get, on my calculator, 1,500 divided by 5,500 is 0.27 with dots over, so I'm going to round that up to 0.3, which is 30%. Let's move on to the next one. So here we've got useful output. Oh, I don't want that colour. I want yellow. I've got my useful output here, 60 joules. Now it's a hoover, so what's useful is the moving, the suction of it, which is the kinetic energy. Kinetic. Okay, the wasted output is heat. Now we've got 460 joules going in, which means we must have 400 joules here of wasted heat energy coming out of this vacuum cleaner. The energy in is electrical. So my writing isn't very good. Electrical. Okay, let's work out the efficiency. Well, the useful output is 60. The total input is 460. So 60 divided by 460 equals 0.13 or 13%. Let's look at the bottom one. We have a TV. The useful energy, or the total energy input, must be electrical again. Let's get the black pen. Electrical. The useful output, well, is 2, because if you want to hear it, it must produce sound, and if you want to see it, it must produce light. we've got to work out the missing value. So it's going to be 211 minus 156 equals 55. Okay, and the wasted is heat. Your TV gets hot. So let's work out the efficiency. It's going to be 55, the useful output by the total input. So 55 divided by 211 equals 0.26, 26%. Okay, right, let's move on to the next one. Okay, I'm not going to do all of these. I'm going to do one of these. Right, let's work out. This is a game console, old-fashioned type. So the useful output is light and sound. That's 75 plus 90 divided by the total input was 275 equals. So that's 165 divided by 275 equals. Get the old calculator out again. It is 0.6. Okay, 60%. So you can have a go at the rest of those if you like. Let's introduce Sankey diagrams. Sankey diagrams are arrows which show the thickness of the arrow shows the amount of energy. So the total input there is represented by the thickness of this line, which is, I think, that's 20 squares. Okay, 20 squares. The useful output is always the horizontal one. So the horizontal one there, let's see how thick that is. Well, that to me looks like 6 squares. Let's get that to be black. 6 squares. Okay. The one that comes down here, the downward arrow, is always the wasted one. Let's have a look at the thickness of that. We've got 5 plus 9. I think that's 14 squares. Let's get that to be black. So we can work out the efficiency because it's 6 squares, which is usefully transferred, divided by 20. 6 divided by 20 is 0.3 efficiency, or 30%. Okay, so you get the idea of a Sankey diagram. Sometimes they're just drawn arrows and they've got the numbers on. Here is a Sankey diagram of a filament light bulb. We can tell it's a filament because it's got this little wire in here. It's called a filament, and these are very inefficient because it's a wire that gets hot. So lots of energy wasted there. So 10 joules is the useful output. Oh, I've done it in black again. 10 joules is the useful output. The total input was 100. So it's 10 divided by 100 is 0.1, 10%. Here is a more efficient light bulb. It's called a fluorescent. Get that in black. Fluorescent. And it's much more efficient. As you can see from the numbers, we've got an output there of 75%. The input is still 100. So 75 divided by 100 is 0.75, 75%. Even more efficient than that is an LED. Okay, but I haven't got a diagram of that on this PowerPoint. If we were in school, we would be doing a practical. We would be measuring the efficiency of an electric motor lifting weights off the floor. So in order to measure the input energy, the electrical input, we would need to multiply. So the power, get that in black, power equals current times voltage. That's the power. So the energy, therefore, is power, which is I times V times time. We would need to multiply the current by the voltage by the time. That would tell us the electrical input power. The output, sorry, that tells us, this here tells us the electrical input energy. Okay, so current times voltage times time. The output energy of this is the gain in GPE. So the output equals the gain in gravitational potential, which is m times g times h, and this up here is the electrical input. Okay, so what does that look like? We do a calculation. Here is an example of a motor lifting a mass. So looking at this, then we're going to work out the efficiency using this equation. The useful output is the gain in GPE, which is mass times G times H. Well, the mass is 0.5, G is 10, the height is 2. So the mass gained 10 joules at the end of this, and that's the useful output. The total input, well, that was electrical energy. So we're going to work out the power times the time. Electrical power is current times voltage. So we've got an 8.1 watt motor here. It was switched on for 4.3 seconds. So the input energy is 34.8. And if you go 10 divided by 34.8, you get 0.29. It's 29% efficient. Okay. You can replay this section of the video if you need to. Okay. But these are the measurements that we would take from the practical. What we would do in the practical is we would change the mass. We would increase the mass. We would measure the input energy, and we would measure the gain in GPE, and we would calculate the efficiency and how it changes. Okay, so it's quite a good experiment, and it does stretch your knowledge of energy types and efficiency. That's all I have time for today. If you need to watch the video more than once, please do. I shall put some questions in the form of a mini test on its learning for you, and I will also put some extra questions there for you to practice as well. So good luck. If you get stuck, send me a message on its learning, and thank you for listening.